And before I forget, I need to advertise. Actually, we are trying to put together, right now it's accepted, a workshop, a long workshop, a program of GPT in 2025. In a year. Okay, please. It's very futuristic. If you're interested, please consider it. So, during the pandemic, with Angel, Victor, and Andrea, and I think we were thinking about writing a perspective of this field. I want to tell you about it because this is actually how I started thinking about it. My background is quantum optics, and I started to do some investigation in correlated material. So, for quantum optics is very simple to understand. You have like a two-dimensional phase diagram. On this one, you have the photon number. On the y-axis, you have the strength of interaction between photons. Basically, light-matter interaction is weak, but then when you integrate out the matter, you get some interaction, weak interaction between matter and between a photon and photon. So naturally, you're in just this weak regime. Photons very weakly interact with each other. And then if you put many of them, consider many of them, then you go to the regime of classical non-reductors, like solitons, like the usual classical non-reductors. So this is because light-matter interaction is weak. Now, if you put that matter into a cavity, and that cavity forms a photonic mode, it can be any photonic mode, then that photon bounces many times back and forth inside the cavity, and then the light-matter interaction is enhanced. Which can be captured by like the finesse of the cavity, in the language of the cavity, QED. So basically now you have enhanced interaction between photons. And then if you have many photons in the system, then you have strong interaction between many photons.
Why is it a dot?
Because of a keynote, I wanted to just find something that is not just a square and has like round shapes and ended up with a dot. Very deep. So there is now a new axis that what if my two-level system is no longer a two-level system? It's an electron that is itinerant and it's interacting with light. How should I think about that? What if those electrons are actually interacting with each other and they form a correlated state? How should I think about light-matter interaction? So you have over here that you have localized two-level system, and then now you have correlated material. It can be a multi-insulator, fractional quantum Hall, superconductivity. So you can tile this system now like this. Yes.
Question: could this an orthogonal axis to make phonons non-linear? You have to couple them to matter.
Photons.
Yeah.
Yes.
So how can we separate pick up the linearity for photons versus?
No. So you indeed can have situation over here that you have correlation between electrons, and now since they're coupled to photons, they induce strong interaction between the photons. It's just the usual way when I was in this two-dimensional system, my electrons were localized. They were just two-level systems, two-level atoms, either a quantum dot. That's one. So here they can be itinerant. They can move around, and then that immediately brings us to some basic questions. How should I think about light-matter interaction? Now, maybe I go beyond dipole approximation. Maybe my electrons actually care about the wave function of the spatial profile of my photon. And so that would be actually the first part of the talk. Second part of the talk is that usually I think about shining light and creating excitons in a semiconductor. They're basically two-level systems. But what if that system is already in a multi-insulating or correlated state? How should we think about these things? So what I'm going to talk about is a mixture of theory and experiment that we have been doing in the past few years. And can be like use optical means to induce interesting states that Andrea was telling us about, like superconductivity, or can we manipulate fractional states of electrons? Can we measure electron correlations by using optical means? So there is a work in progress that my student Galton is over here. So I don't know whether he's going to talk about that work in progress, but that's it. So The talk has two parts. The first is this light matter interaction behind dipole approximation, and in particular when the electronic wave function can zoom around and then be larger or comparable than the wavelength of light that is relevant for that transition. And then the second part is to how to think about excitons in a correlated material, which is going beyond the usual semiconductor excitons. Okay. So in quantum optics, we usually do this dipole approximation. The wave function of the electron is much smaller in extent, in spatial extent, than the wavelength of light. That is usually because of either Coulomb confinement, like the Coulomb interaction. You have an electron and hole, and then they form a hydrogen atom, like atom in matter, or if you are dealing with a real atom, that's the case, the Bohr radius is much smaller than the wavelength of the corresponding. In the language of matter, you don't transfer any linear or angular momentum when you're shining light through. But if the electronic wave function for some reason is comparable to the wavelength of that transition, then we should expect some effect. Okay? So the manifestation of it can actually happen in superconducting qubits, and Andre is in the audience. He has a poster if you're interested, but I'm not going to talk about that. I'm going to talk about the quantum Hall manifestation. So let's go back and see what happens beyond this dipole approximation. If you just have a simple atom, you have this dipole transition from S to P and then P to D. But you don't have an S to D transition because that's dipole forbidden. Meaning that you need like two angular momentum, two quantum angular momentum to go from S to D state. And that's actually a very nice experiment in the group of Schmidt-Feller and Mainz that they did this experiment. They had an ion, and they did a direct transition from S to D by shining a light that not only has a sigma plus sigma minus polarization, but also it has an optical vortex. So each photon that is absorbed, it gives two H bar. One coming from just the polarization, the other one just from this angular orbital angular momentum. So naively we would say, okay, we can do the same thing for excitons, and we spent some time wasting and thinking about this so that it's possible. So you can go from ground state to S wave exciton or now to P wave exciton by shining these kind of optical vortices. But the answer is actually no, or it's harder than when we think. Is that imagine that I shine light on a piece of semiconductor. Now I create excitons everywhere. I cannot confine the excitons. Excitons are created wherever I shine light. So some of these excitons are created here, some of them are created here, and depending on where they are, they can appreciate this phase gradient more or less. So the guy who's over here maybe actually appreciates a phase gradient much more than the guy over here. So most of the response in the end would be just dipole response, and then maybe a few of them in the middle would see these kind of P-wave excitation. The reason is that again the dipole, the Bohr radius of this exciton is small. So the angular momentum that I'm imparting with light would go to the center of mass, not the relative coordinate. So you can basically think of it that you shine light and it has a vortex and it would start steering these excitons. This is the same in cold atom. You can actually have a condensate, you shine light with orbital angular momentum, and then you can steer the condensate. Yes?
This first atom, this is two-photon process, right?
So indeed, it's a single photon process.
Single photon.
Yeah. So of course you can do a two-photon process by doing two dipole transition.
Yeah.
But the novelty of it is that it's actually a single photon transition, but you go from S to D. So can we see this in material? So quantum Hall, we go to quantum Hall states. We should expect some states that are extended. And then in a regime that Coulomb binding is not present. And then we hope that there are some wave functions that are large enough, and it's determined by the disorder landscape. And then they can be shifted. So imagine that in absence of disorder, I have two Landau levels, Landau level 0 and Landau level 1. And then M describes the angular momentum of this Landau orbit. This is in the symmetry. So you can think of it in terms of Fermi-Goldman's rule. You're shining some light, and you're looking at the light-matter interaction. This is the initial state, and this is the final state. Random level 0, 1, and then M characterizes this angular momentum. So M it tells you how much these states are going. M and M. Now, what I put in the middle, this is for graphene. So basically, you can think of it as P dot A that has been written this way. And then A, we usually just reduce P dot A to E dot E and do the typal approximation. Now we want to take care of the angular momentum of our electric field. So in particular, we can write it in the cylindrical coordinate. So it would have some form like this, e to the I L theta, L now being the angular momentum of this light field. And then some Bessel function that describes the radial form of our solved maximum equation in the cylindrical coordinate. So you go from M to M plus L to M prime. That's the selection rule that just comes from the angular part of this integral. And then the radial part of this integral will tell me whether the quadruple and higher orders are there. So I can go from M to M by just absorbing a sigma plus or sigma minus line. But I can go to M plus 3 or M plus 4 if the angular overlap, if the radial overlap allows me. So these are allowed through the angular part of this integral, but the radial part of the integral will determine whether these transitions are relevant. So in the quantum Hall, for those who are a little bit familiar, is that when you go to higher M, they become more squeezed. So M plus 1, M plus 2, M plus 3, they almost have the same spatial support. And then if your light has some overlap over that support, then you can expect that these transitions are non-negligible. But as I said, this is in the absence of disorder. We can put some radial symmetry. So now, what would be the manifestation of it in an optical experiment? Imagine that you have two Landau levels, Landau level 0 and Landau level 1, and these are the angular momentum of those states that are related to the radius. So larger M would be further away from the center. So you shine some light that has non-zero orbital angular momentum, this light vortex. So you go from M to M plus 1, so like 1 to 2 to 3, etc. You have excitation, but then after that you have relaxation. But the excitation is preferential, the relaxation is democratic. So you excite them, and then they democratically go back to the initial state. But if I keep doing it, I've moved the population from the lower radii to the higher radii. So this is very similar to the optical pumping that we do in an ion in an atom. Over that, we do it in the hyperfine states of the system. You start from like minus M and then you come to plus M. Here in the is an external equilibrium of your electron, because the electrons I can assume them to be not conformal. So with this, you can do a back of an envelope calculation. How many photons I need to move a charge from the inner part of the sample to the outer part of the sample. So it is similar to Lofton's argument, but it's a bit different. So Lofton's argument is adiabatic. Here we are looking at a non-adiabatic process. But it smells like that. So how many photons I need? Each photon will impart angular momentum n, and then the maximum number of angular momentum that I have in the system is m. So I need to impart m angular momenta such that I go from the inner edge to the outer edge. Then the power of my laser is given by the frequency of these photons and the number of photons, the duration of their exposure, and that will give me a current. So you should expect a radial current that is proportional to the power and this angular momentum. And the direction of this radial current should be determined by the velocity of it. So the lights have the same spatial form, but they have different vorticities. So this is experimental results. so you can look at the radial current. This is the radial current as a function of bias voltage. We also apply a bias voltage to the radial bias voltage. You can think of it in the beginning that would be 0. And now if you switch the vorticity of light, you will see that the photocurrent would change and they're different. So of course when you shine light, you generate photocurrent regardless of that. What is important is that when you switch the orbital angular momentum, there is an appreciable shift. And then now we can tilt the system radially by doing this bias voltage. We see that when we tilt that, of course the overall current changes, but there is an appreciable shift in. Now, if we subtract this, you will see that there is this difference for here and I test. Now you can say, well, that might be just due to the fact that you're shining more plus light than the minus light. You miscalibrated your system. So the blue light was generating more current. But you can keep the same profile, but then flip the magnetic field. And then you will see that the photocurrent will change. So certainly it's not just about calibration. One can also do more control experiment to look at whether this is due to polarization or due to the angular momentum. You can change the polarization of the system, go from circular polarized to linear back to polarized, and then you see again the offset remains the same. This is valid for both angular momentum 2 and angular momentum 1. Naively, you would expect that for angular momentum 1, you get the smaller effect than angular momentum 2, because angular momentum 2, you're imparting twice that angular momentum. But we didn't see it in the experiment. And the reason is related to the spatial overlap. We are we're shining like a Laguerre-Gaussian field. And the Laguerre-Gaussian radial profile actually changes as a function of that. So the radial overlap of our sample was reduced for angular momentum. Then one can look at it as a power and then see whether it increases linearly. So we are still in the linear response regime, meaning that we are not seeing any Pauli blockade effect. You start doing it faster and faster. So this is so just before this. So this kind of like shows one example that this particle approximation can be violated, and these electrons not only care about the intensity of light, but also about the phase of light. The picture that I started with was in the quantum Hall picture. It's very nice to see this orbital angular momentum, etc. But we are looking at graphene in a strong magnetic field. The Landau levels are very close to each other. So for a large part, you can think of it as just an electron in a magnetic field, like a Dirac electron in a magnetic field. And that is actually the case. My colleague Jay Sao actually developed a picture as well like that. So we can have this Dirac fermions plus magnetic field, and then it can again explain the effect that we are seeing. But again, you have to go beyond particle approximation. So the electron actually cares about this spatial. So now the next step is that how much we can actually push this. This means that this light matter reaction cares about the phase of the electron. If the electron was localized, if it was a bunch of quantum dots, we would not have seen this effect. It means that it actually cares about the electronic coherence. To what extent we can push this technique to measure the spatial coherence under an electronic wave function. And then, if so, can we look at some other questions? Can we look at like a transition between quantum Hall controls and optic? Like the previous talk, this is an experimental observation. We have some theory, but of course the physics is way more complicated than that. And one of them is many Landau levels that I mentioned that we're looking at graphene. Another idea would be just to use gallium arsenide and look at the either interband transition or interband transition. I'm sure Jerome will tell us about the interband transition. And maybe actually some of these effects would be relevant for the experiment in cavity. That's to be discussed. Okay, so that concludes the first part of my talk. How much time? Sorry. Okay, questions? Yes.
So once you have a disorder, the angular momentum is not a good quantum number anymore, so
Correct.
you'll still have this counting.
Yes, so I think of it as this, that if I put, actually that paper, that theory paper includes the disorder. So as long as I have some state that it's winding and then it sees the space gradient, it's enough. As long as they're extended, they don't have to have the exact shape.
Maybe I'm confused, but you showed that you have more transport when L equals plus minus 1 rather than...
Yes.
But then isn't that the same as just using plane wave? Because you only are using plus minus 1 change, right?
No, plus minus 1 angular momentum.
Oh, not
yeah.
M.
So there is a polarization, sigma plus sigma minus, and on top of that we have this L plus L minus. Jerome and
Sorry, quickly, you have to satisfy a resonance condition in terms of photon energy, or for the specific magnetic field you're using, or?
no, so as I said, so this is, we are talking about like the Landau level number 30 and 30 plus 1. So it's almost, there's almost a continuum.
So you emphasize that the Taos pump being non-diabetic here.
Yes.
What is the effect that we're seeing actually from that being non-diabetic?
The recombination. So we create this electron hole pair, and then the picture that we have is that we produce some polarization in the system, and that polarization cannot be, you cannot get rid of this polarization very easily. Every time you're creating this polarization, and then you're moving it. But then the more complicated picture comes that this electron and hole, the way that they recombine and get to the Fermi surface, depends where you have put your vacuum. Whether your Fermi C is in the middle of a Landau level or is in between Landau level. So those are the complications. I'm happy to discuss about it. Yeah.
Actually, to follow up on the same, do you see any accessibility x-axis when you do this?
Yeah, so you can. So there is. So just a quick one is that this is the Corvino, so you don't have any edge. So indeed, you will get the suppression of resistivity at when you're in the non-zero. When you're in the non-zero sequences. So you just have two terminals. Well, there is a dependence on that, and there is this bottleneck effect that it really matters where you are putting your Fermi. But hopefully those things would not happen when you're just looking at 0 and 1, like in terahertz or in N1. Yes.
So you mentioned earlier there's a single photon with vertex that can excite angular momentum by 2. So what's the difference between two photon process besides the similarities as change angular momentum? For example, can I use this noble single photon with vertex to excite like to the Plancke mode of correlated fraction quantum states?
So, okay, very, very good point. So the question is that can I impart an orbital angular momentum? Can I like excite states that have non-zero orbital angular momentum, create and manipulate anyons? I didn't even mention that because we are still trying to understand the single particle picture, but that certainly is the holy grail, whether you can optically excite things. So I will move to the second part. And the second part is about the excitons. Usually excitons weakly interact with each other. So this is gallium arsenide pillars from Jacqueline Bloch's group. And then you can write Bose-Hubbard model for them. But the interaction is usually weak. Then the way to enhance this interaction is actually to confine the Vanier orbitals. This is actually a very familiar story for folks in cold atom. Atoms interact weakly with each other, you put them on an optical lattice, and then you enhance basically the interaction. Here is the same. So if I now confine my excitons using a superlattice structure, here it would be a Moiré superlattice, then you should expect the same thing. So what I'm going to talk about is in this transition metal dichalcogenide Moiré bilayer semiconductors. There is actually now a recent work in gallium arsenide and photons using electrons. So the idea is that, again, we have 2 layers of semiconductor. And then since there is this lattice mismatch, you can twist it. Or sometimes you don't even need to twist it if the dicot coefficients are different. Then you actually create a superlattice structure because they have to match each other. You put them on top of each other. One creates a superpotential for the other one, superlattice potential for the other. Here we are interested in the interlayer excitons. That the exciton is in one layer and the hole is in one layer. They recombine and emit a photon. And you can put the Fermi level over here. You can look at the photoluminescence, which basically means that you create an electron-hole pair. You put the electron in one layer and the hole will go to the other one. They create an exciton and they will emit a photon. And there are many interesting experiments that have seen multi-insulating states of electrons and holes at Cornell, Columbia, and ETH. So we were interested to see whether we can actually look at the strong exciton interaction. You can think of it in this basically phase diagram, and the x-axis is the electron density per cell in this more superlattice potential. So you go from 0 electron to 1 electron per side. And then the intensity basically sets the number of excitons that you have created on these sides. So if you have not many excitons created and then there are no electrons in the conduction band, these excitons are alone, you create them, they dissipate, and then you see a peak in the photoluminescence. Now if you dope the system and you put 1 electron per side, and if you want to create now another exciton, then you have electron-electron interaction, or in particular, you have an exciton-electron interaction. And the energy of this emitted photon should be different than this one. So you should see a jump when you arrive over it. You can also dope the system, not electronically, you can dope it, you can photodope it. You can now increase your intensity of the input pump. So some of these sites are populated with excitons, some of them are populated with electrons. So again, if you exceed some number, then you should see a jump in the luminescence spectrum. So you should see that energy gap. And that's what you actually see in the experiment. So so this is the gate voltage, which basically characterizes the density of these electrons. If there are no electrons in the system, then you see a peak like this. But now if you put 1 electron per side, you should see a jump, and this is a very large jump. It's kind of amazing how large this jump is compared to the line length of this system. Usually, in order to show something that this driven dissipative systems are good for anything, and we create a correlated system, the interaction should be larger than the dissipation, and then here you see that is the case. Now, if you start putting more and more photons in the system, that line would jump at the lower Finite factor. So here, over here, so you can see this in an animation that this we are. If you see it over here, we are increasing the number of excitons that we have created in the system, and the system would jump to this X2 line at an earlier time. Okay. We can also think of them as this was just that jump. We can also look at the profile as a function of the total PL power that we put in the system, whether this X1 would saturate and then X2 would saturate. You can think of them as a shell. So we put one exciton per site, and then once it's filled, we go to the next shell. And then once that's fixed, we go to the next shell. Yes, there was a question.
Yeah, sorry, this is a naive question, but why do you see such discrete jumps and not, say, as you change the gate voltage, why is there no start effect of any sort?
Maybe you don't mean the start effect, maybe you mean like a mean field shift.
Sure.
Yes. So if the tunneling is 0, imagine that the tunneling is 0 for the moment. Then each site has, just I can individually look at them, and then they should have one transition at the X1 and then one transition like this.
Very discrete.
So we think that we were in a very small tunneling. Tunneling is estimated to be 1 order of magnitude smaller than u. There is another subtlety that I will come back to it after the output.
Maybe it's just my eyes, but so you have in the first plot you showed, you have the jump from one to the next, but it looked like there was almost a little arm extending before the jump.
Very
Is that
good.
just a trick?
Okay, we don't understand everything, so that's, it's over here actually. So there are two jumps, in fact. One jump is that if I have an electron and then I create an exciton, it should have one jump associated to exciton-electron interaction. The other one should be exciton-exciton interaction. So maybe it's because of that. But there are actually two jumps. One is that if I have an exciton and now I want to put another exciton, that would be more like a Hubbard U, Bose-Hubbard U, and then this would be but I don't want to sign on this. This will be exciton-exciton. Yeah. Yes.
And is it active or repulsive?
Repulsive. It's a fusion. So this is like a simple picture. We did also some diffusion measurement to see that how these things are going on. This is like really the first round of diffusion measurement. Physics turns out to be more complicated. So what you do is that you shine some numbers in a pump, you create this electron hole pair, and then at some point they emit, and then you look how far they have made it. So in a very cartoon picture, you can think of them, there's no one around, I create my exciton happily, and then it diffuses. It can diffuse like a classical particle, or if it's or random walk. We still don't know that whether actually which one is the case. But we expect that when we are getting to this bosonic multi-insulating phase, then they should block each other. Meaning that if I have now this exciton, they cannot be easily diffused because they're blocked. Then we see some indications of that. So this is the diffusion distance as a function of the doping of the system. So when the system is not doped, you see this general trend. You increase the pump power, the excitons repel each other further and further, so the diffusion gets longer. But then at some point you see the opposite trend to happen, and then we associate this to have some interaction. Do we have a full understanding of this? No. Do we have like a full picture of whether these excitons, whether it's like diffuse it, self-diffuse it, etc.? No. One particular complexity over here is that when you're doing this this photoluminescence, is that you create this electron hole pair. They are very hot. They are in a plasma mode. We don't know whether they recombine, they form an exciton, and then they would move in the system, or no, actually they move as a hot plasma, and then they form an exciton. So right now we are trying to understand which process is done. But initially we thought that, this is very cool, it's just like a two-level system, hard-core bosons, related to that question, that they can have either 0 or 1 excitation in the system. So you can think of them as a 2D array of spins, and it's in a driven dissipative limit physics, so we can explore some driven dissipative wedding cake. This is a wedding cake made by AI. I asked, make a wedding cake with super fluid, and then it came up just quite good. Can you have this system and now confining the cavity? The other team of this workshop, the answer is actually yes. You can actually use monolayers of these TMDs to make a mirror that was shown at ETH at Harvard a few years ago. And now recently with my colleague's group and my group, Yojo, we showed that we can actually make a cavity. If you have one monolayer that acts like a mirror, if you put two of them, it makes a cavity. But it's a funny cavity. It's a narrow band cavity because it only responds on the resonance. So you can think of putting these actually in the middle and then form now a cavity. And you can go further, and then you can think of fractional shell insulator of excitons, etc. But let's go back and understand how these excitons, 5 minutes, okay, I have to a little bit speed up. So the usual exciton story is like this. You have electron hole pair, you create a bound state below the continuum, and that's it. What about these guys that are correlated? How should they think? It's not just a free electron and a free hole that bind together and just solve that two-body problem. So in general, it's a difficult problem. But let's just focus on a simple example of this Moore exciton. This is the work by my student Sang Sheng and Peter, who used to be at UMD, and now he's over here. So if I have these excitons sitting in a lattice, in a confined lattice, if the Bohr radius is much smaller than the Vannier orbital, I can think of them as good bosons. I can put one after another, etc. And then they're happily over here. They can write it honest to nature commutation relation for these excitons. But if the Bohr radius becomes larger than this Vannier orbitals, then they become basically fermionic. You cannot put two of them on top of each other. This is what I'm just saying is Pauli exclusion. If you turn off the interaction between electron and hole, it is a Pauli exclusion. So you have it. Is any of this physics relevant to this TMD exciton? The answer is yes. And that Bose-Hubbard model that we wrote is not really relevant. That's basically what we learned. So in the interest of time, I'll just briefly say that, okay, so we basically solve this electron hole pair problem in the presence of a potential. So usually you don't have this Moore potential, you just have a dispersion. And then you have the dispersion, Coulomb attraction, and then you solve a two-body problem. And make Vannier excitons. You can call it the Bethe-Sackvittel equation, or a short Schrödinger equation, doesn't matter. Here it's just a little bit different. You have this lattice on top of it. So you find these orbitals, they're in this lattice structure. You take the Fourier transform, you create the Vannier orbitals. So now you have the creation of an exciton that is characterized by this integral, creating an electron and a hole in the valence, conduction and valence time respectively with some form. And now you see that when you look at the commutation relation of x and x dagger, it's not one. And in particular, if you look at that and it's commutated with x dagger, it becomes something that is not. So if lambda was 0, it would have been a good old exciton. But now it's not. And the same integral that happens in exchange interaction is basically this level. Is it relevant for experiment? The answer is yes. So these two pictures that I showed in the beginning, you can actually look at them as a function of Bohr radius with respect to the Vannier orbital. And the experimental relevance, for example, for tungsten bisulfide, tungsten bisulfide, as a function of twist angle is the following. So this lambda is not 0, it's appreciable. And this means that we can put a finite number of these bosons on each side. In particular, for some twist angle, it's 2, and in some situations, it's 3. So it's basically a boson with this hardcore interaction. You can define this effective. They look like angular momentum, but they're not exactly. You can do also Trimakov, and then write an effective interaction. So they're actually interesting things. We thought that they were just Bose-Hubbard model, but it turns out to be way richer than Bose-Hubbard model. So they're good for stuff. This three-body interaction, or the three-body interaction is actually apparent Hamiltonian for many correlated states. So it might be actually an interesting feature for the systems. So I don't have time. The last part was about what Eugene and collaborators have worked a lot. So he can tell you more about this than me. It's just to create these excitons now in the presence of a correlated state. So I was just talking about this charge order so far. But imagine that I have an antiferromagnetic system. I create a hole over here and an electron over here, and then now I have this exciton, but its tail is a hole that is in the bed of this antiferromagnetic state. So the diffusion of this exciton should fill this antiferromagnetic state. So right now we are trying to understand whether by doing diffusion measurement of these excitons. One can be correlated and ferromagnetic. So with that, I just want to summarize. The first part, I talked about this young dipole approximation physics, that since it's actually relevant, one might be able to use it. The second part is this formation of exciton correlated system. I acknowledge many of the folks involved on each slide, but I wanted to highlight the first experiment was led by Derek Session, my graduate students, and Mahmoud Jalabi, my postdoc. And the second experiment was led by these three folks: Beni as a graduate student, Daniel as a postdoc, and then Supra. Thank you very much.
Only time for a couple of quick questions.
So just the lambda levels would be just one, different by one, each lambda.
Yeah, they all have the same Chern number,
Yeah.
but if you have a band structure where you excite to a higher band that has a different Chern number than the one you
express that's how it fits. Three-dimensional.
Suggested to stop here and continue our bottom.
That's right.
Mohammed.